it's pretty wild when you look at the projections for CO2 emissions going forward.
Yeah.
I mean, 50 billion tons a year by 2050.
Wow.
Atmospheric concentrations way up past 500 parts per million.
It's a
lot.
It's a lot, yeah.
It paints a pretty urgent picture,
For sure.
So for this deep dive, we're focusing on something that could really make a difference going forward.
Okay.
Direct air capture, or DTAC.
Right.
And what's so cool about DTAC is that, unlike other things, it's not tied to a specific emission source.
Right.
It can be deployed anywhere.
Yeah.
And can actually pull CO2 right out of the air.
Yeah.
So this gives us a way to actually achieve negative emissions.
Yeah, absolutely. And it's important to note that we've had methods for capturing CO2 for a while,
Right.
particularly at industrial sites.
Yeah.
But DTAC really presents a totally different set of opportunities.
Well.
And, traditional liquid absorbents, they're okay to a degree, but they often need a lot of energy to regenerate the CO2 that they've captured.
Right.
And, they can degrade over time and lose their effectiveness.
Right.
And then there are some concerns about secondary pollutants even.
Oh, wow.
So all this has really got researchers looking more into solid materials as an alternative.
Okay.
Specifically, solid amine adsorbents.
Okay, so solid amine adsorbents.
Yeah.
What makes them so promising compared to the liquids?
Well, compared to liquids, solid amines usually need less energy to regenerate.
Okay.
So that means we can release the captured CO2 a lot more efficiently.
Oh, yeah.
They also tend to be more stable over multiple capture and release cycles. And that brings us to what we're really talking about today, metal organic frameworks.
MOFs.
MOFs, yes.
I love it when we get to talk about MOF.
Wait.
So you could think of them as like really tiny, highly structured cages at the molecular level.
Yeah, that's a great way to put it.
Okay, cool.
Yeah.
Now, we have talked about MOFs before on the show.
Yes.
But can you remind us why everyone's so excited about them for capturing CO2?
Sure. So MOFs are made from metal ions that are connected by organic molecules.
Right.
And that creates these materials that have really high porosity.
Okay.
So if you can imagine like a super lightweight sponge,
Okay.
but with pores at the nanometer scale.
Wow.
That's kind of what we're talking about here.
So lots of little tiny holes.
Yeah, exactly.
Okay.
And what's really amazing is that we can fine-tune their properties.
What do you mean by that?
Well, we can engineer the size and the shape of the pores.
Okay.
We can create these huge internal surface areas.
So more places for the CO2 to stick.
Exactly.
Okay.
And we can even chemically modify the internal surfaces to really attract those CO2 molecules.
Oh, wow.
So we can kind of custom design them at the molecular level for this very task.
It's like we're building custom designed traps for these CO2 molecules.
Yeah, exactly.
That's so cool.
It's really remarkable.
So there are all kinds of MOFs out there.
Yeah, there's a huge variety.
But the MIL series,
Right.
the materials of Institut Lavoisier,
Right.
those seem particularly promising for Dara.
Yeah, they really do.
So today we're looking at one in particular, MI-100 CRD.
Yes.
What makes this one so special?
Well, it has a really impressive surface area and it's super resilient.
Okay.
It can be exposed to air moisture and even high temperatures, and it just doesn't break down.
Wow.
Studies have shown that it can stay intact even after being in water for a long time. That makes it really good for attaching those amine molecules that are going to grab the CO2.
So MIL-100 CR is like
Yeah.
the strong foundation, and we're attaching the amine molecules to it to do the work.
Exactly.
So the goal for this deep dive is to find out how well this actually works.
Yeah.
How good are these amine-functionalized ML100 CR materials at pulling CO2 directly from the air?
Right.
And the research we're looking at today looked at a bunch of different amine modifications, right?
Right. They did a systematic evaluation
Okay.
using ML100 CR. That was modified with 3 different amines. Polyethylenamine, or PEI.
Okay.
Tetraethylenepentamine, or TEPA.
Got it.
And diethanolamine, or DEA.
DEA. Okay,
Yeah.
so 3 different ones.
Yes.
And they used something called impregnation to get those amines into the MOF's pores.
Right.
And for all 3, they kept it at 50 weight percent.
Yes. 50 weight percent for all of them.
Okay, so why 50%?
So that 50% loading, that was determined in some earlier experiments.
Okay.
And they found that if they went lower with the DEA, say 40%,
Yeah.
the CO2 capture was just too low.
Not worth it.
Yeah, not practical.
Okay.
But on the other hand, when they tried to load the PEI at 60%, they had problems with it clumping together.
Oh, so it was getting in its own way.
Exactly. The clumping blocked some of the capture sites. So 50% was like the sweet spot.
Okay, so it maximized how much amine was in the MOF.
Right.
But also made sure that it was spread out enough to do its job.
Exactly.
Okay, so they've made these 3 different materials. How did they figure out what they had made and what it could do?
Well, they used a bunch of really cool techniques.
Okay.
First, they used X-ray diffraction, or XRD.
Okay.
You can think of this as a way to see the crystal structure of the material.
Okay, so like the skeleton of the MOF?
Yeah, exactly. And the XRD results showed that the MIL-100 SER framework was mostly still there.
Even with the amines added?
Yeah, even with the amines.
Okay, that's a good sign.
Yeah, it means it's stable.
Right.
There was a little decrease in the intensity of some peaks.
Makes sense. You're putting stuff in those pores.
Exactly. It's going to change things a bit.
Okay.
What else did they do? Then they used Fourier transform infrared spectroscopy, or FTIR.
FTR, okay.
This helps us figure out what kinds of chemical bonds are present by looking at how it absorbs infrared light. So the FTIR spectra confirmed that the original MIL-100 CR structure was still there.
Right.
But importantly, they also saw new signals that matched the carbon-hydrogen and nitrogen-hydrogen bonds.
Which means
the PEI-TEPA and DEA molecules were there.
Okay.
Like they saw these specific bands in the 2800 to 3000 wave number range, showing CH bonds.
Right.
And a band around 1613 for the NH bonds. And they even saw CN and CO stretching vibrations that were specific to each amine.
So like a fingerprint for each one.
Exactly. It confirmed they were in the MOF.
Awesome. So they know what they put in there.
Yeah.
But they look at the pores.
Yeah, they did nitrogen adsorption analysis.
What is that?
So this is how scientists measure the surface area and pore volume by seeing how much nitrogen gas the material can absorb at really low temperatures. And as you'd expect, they saw a big drop in both the surface area and pore volume after adding the amine.
Okay, so the amines are taking up space?
Yeah, basically they're filling those internal spaces.
Okay.
And interestingly, the PEI modification had the biggest effect.
Because?
Probably because PEI is bigger.
Oh, the polymer chains?
Yeah, they take up more space than TEPA or DEA.
Right, so like our sponge analogy.
Yeah.
We're filling some of the holes, but the sponge itself is still there.
Exactly. The MOF's structure is still intact.
Okay.
And they also looked at it under a microscope.
Oh, really?
Yeah, they used scanning electron microscopy, or SEM.
SEM, cool.
And energy dispersive X-ray spectroscopy, or EDS.
Okay.
And the SEM images showed the particles got a little smaller after adding the amine, but the overall shape stayed the same.
So again, the amine is mostly going inside the pores.
Right.
Okay, what about the EDS?
So the EDS was really helpful because it let them map out where the elements were.
Okay.
And it showed that the nitrogen from the amines was spread evenly throughout the MOF.
Okay, cool.
And the PEI had the highest ratio of nitrogen to chromium.
Interesting.
Chromium's a key part of the MIL-100 CR.
Right.
So that means there's more amine in there.
Okay, so they have all these different ways of confirming the amines are there.
Right.
And how they're interacting with the MO. Okay, so the big question is, how good are they at capturing CO2?
Right, so that's what they really wanted to know.
Yeah.
So they measured the adsorption capacity.
How much CO2 it can hold.
Exactly.
Okay.
And the best one was the MIL-100 CR, modified with PEI.
The PEI, okay.
Yeah, it had a CO2 adsorption capacity of 1.21 millimoles per gram.
Okay.
That's 2.5 times better than the unmodified MIL-100 CR.
Yeah.
Which was only 0.48.
That's a big difference.
It is.
Okay, so PEI is the winner so far.
Yeah, it is.
Why is it so much better?
Well, it comes down to its chemical structure and all that nitrogen.
Okay.
PEI has a lot of branches.
Uh-huh.
And those branches have tons of amine groups.
Okay.
And those are the things that bind the CO2.
Right, so more amine groups, more CO2 it can grab.
Exactly.
So that's why PEI is better than DEA.
Right, DEA has way fewer amine sites.
Makes sense. Okay, so they capture the CO2,
Uh-huh.
but then they have to release it to use it again, right?
Yeah, that's super important.
Like, how did they look at that?
So they used CO2 temperature programmed desorption.
What is that?
So basically, you heat up the material in a controlled way, and you see how much CO2 comes out at different temperatures.
Ugh.
And what they found was interesting. The DEA released its CO2 pretty quickly and at a low temperature.
Of how low?
Around 45 degrees Celsius.
Okay.
Probably because the CO2 wasn't bound that strongly to the DEA.
Right.
Maybe because it doesn't have as many amine sites.
Okay.
And it also might have something to do with hydroxyl groups on the surface.
Interesting.
But the TEPA and PEI, they release CO2 at higher temperatures.
Okay.
Around 70 and 90 degrees Celsius.
So they were holding on tight.
Yes. So the researchers decided that 80 degrees Celsius would be a good regeneration temperature.
Okay. So it's hot enough to get the CO2 out.
Yeah.
But not so hot that it damages the material.
Exactly.
But then you have to do it over and over again.
Right.
So how did the materials hold up after multiple cycles?
So yeah, cyclic stability is essential.
Yeah. If you have to keep making new material, that's not good.
No, not at all.
Okay.
So the PEI-modified MIL-100, CR. It was super stable.
Right.
It kept over 90% of its CO2 capture capacity after 20 cycles. Yeah, and its average was 1.18 millimoles per gram.
Still really good.
Yeah.
What about the others?
So the DEA, it didn't do so well. It lost over half its capacity after 20 cycles.
Wow, that's a big difference.
Yeah, and they looked at them under the sea again.
Okay.
And the PEI and TEPA looked fine, but the DEA had some poor collapse.
So it was actually falling apart.
Yeah, basically.
Okay, so PEI wins again.
Right. It can capture a lot of CO2.
Yeah.
And it can do it over and over again without falling apart.
Perfect. Okay, but there's one thing we haven't talked about.
What's that?
The air isn't dry.
Oh, right. Humidity.
Yeah. So how does that affect things?
That's a great question. And it's really important for real-world applications.
Right.
So they did these CO2 breakthrough experiments.
Okay.
Under both dry conditions and with some humidity.
How much humidity?
3.1 volume % water vapor.
Okay.
And the results were pretty surprising.
Really?
Yeah, for all three materials, the humidity actually made them better.
What?
Yeah, they had longer breakthrough times.
Okay.
And they captured way more CO2.
But I thought water would compete with CO2.
You'd think so, right?
Yeah.
But there's some really interesting chemistry going on here. They used in situ drifts to look at it at the molecular level.
Okay.
So under dry conditions, they saw carbamate and ammonium carbamate forming. Okay. Mostly from the CO2 reacting with primary amines.
Okay.
But with the water vapor, they saw something new.
What was that?
Bicarbonate ions.
Okay.
So the water is actually helping the amines capture the CO2.
Wow.
Yeah, it's making the whole process more efficient. So instead of a 0.5 to 1 ratio of CO2 to amine in dry conditions, it becomes more like 1 to 1.
Okay.
And that leads to bicarbonate.
Interesting.
And they still saw the carbamate peaks.
Okay.
And more carbamic acid.
So what does that mean?
Well, it seems like the water vapor might also be helping the secondary amine sites become more accessible.
So basically the water is making everything work better.
Pretty much. Yeah.
That's amazing.
It is. And it's really important because it means we might not need to dry the air first.
Oh, wow.
Yeah, that could save a ton of energy and money.
That's huge.
It could be a game changer for DA.
Okay, so humidity is good.
Yeah, surprisingly.
But what about oxygen?
Yes, the other main part of air.
Yeah, could that be a problem?
Well, it could.
How so?
Oxygen can degrade the amines.
Okay.
And then they won't capture CO2 as well.
Right, so they tested that too.
Yeah, they did cyclic testing in air with 21% oxygen.
Normal air.
Yeah, and 400 parts per million CO2.
Okay.
And guess what? The PEI was the most stable again. Yeah, it kept 98% of its capacity after 20 cycles.
So it can handle the oxygen.
Yeah, it seems so.
What about the TEPA and DEA?
They didn't do as well. TEPA lost about 17%.
Okay.
And DEA lost over 60%.
Wow, PEI is really tough.
It is.
But why?
So they used in situ drifts again.
Okay.
While exposing the materials to oxygen at 80 degrees Celsius.
Okay.
And for all three amines, they saw these new peaks.
What were those?
They were amides and amines.
And what are those?
They're non-alkaline products that form when amines react with oxygen. And the problem is they don't react with CO2.
So they're basically useless.
Pretty much, yeah. And the interesting thing is the peaks for these oxidation products were much weaker for PEI.
So it was resisting the oxygen better.
Yeah, it seems that way.
What about DEA?
That one was weird.
How so?
It didn't really show a strong peak for these oxidation products.
Even though it was falling apart in the other tests.
Yeah, it's strange.
Maybe it's because it doesn't have many primary amines.
That could be it.
Or maybe because it doesn't have much secondary amines either.
Yeah, those are usually more prone to oxidation.
Okay, so they also did XPS, right?
Yes, X-ray photoelectron spectroscopy.
What did that tell them?
So that gave them even more information about the surface, like the chemical composition and the electronic states of the elements. And the first scans confirmed what they already knew.
Chromium, oxygen, carbon.
Yep, and nitrogen in the amine-modified samples.
Yep.
But then they looked closely at the chromium 2p spectrum.
Okay.
And they saw that a specific peak decreased and shifted.
After adding the amines.
Yeah.
What caused that?
So they think it's because of the nitrogen in the amines bonding with the chromium in the MOF.
Interesting.
Yeah. This interaction basically increases the electron density around the chromium.
Okay.
And that might create more active sites.
Right.
And guess what?
To wait.
PEI had the biggest shift and decrease.
So the strongest interaction.
Yeah.
Interesting. Okay, what about the nitrogen?
So the nitrogen one's spectra showed peaks for the amino groups and for the ammonium groups.
Okay.
And again, the PEI sample had a more intense peak.
Okay.
So it had more of those primary and secondary amines.
And those are the good ones.
Yeah, they are.
Okay, so all this basically confirms that PEI is the best.
Yeah, it really does.
Because it has lots of nitrogen.
Right.
And it interacts strongly with the MOF.
Exactly.
So to sum it all up, what are the main takeaways about using amine-modified MIL-100 CR for DI?
Well, I think it's safe to say that MIL-100 CR modified with PEI has a lot of potential.
Okay.
It had the highest CO2 capture capacity, grid cyclic stability. It actually worked better with humidity.
Yeah, that was a big surprise.
It was.
And it was the most resistant to oxidation. PEI is the clear winner.
Yeah, it is.
Okay, and all this is because it's got all that nitrogen.
Yep.
And it forms a strong bond with the MOF.
Exactly, and that helps protect it from the oxygen, too.
So this is a really big step forward for D-Day.
It is. It's very promising.
But what are the next steps?
Well, they need to do more long-term testing.
Under real-world conditions.
Yeah, exactly. Different temperatures, humidity.
Right.
Different things in the air.
Okay.
And they need to figure out if it can be scaled up.
Make a lot of it.
Yeah, and see how much it would cost.
Right, because if it's too expensive, it won't work.
No, it won't.
Okay, what else?
They also need to figure out the energy requirements for regeneration.
Heating it up to release the CO2.
Yeah, and the environmental impact of the whole process and how to store or use all that CO2.
Yeah, where does it go?
Exactly.
So there's still a lot to do.
There is, but this research is a great start.
It is.
It gives us a lot to think about.
For sure.
Like, what are the next crucial steps to make this work in the real world?
Yeah.
And what other things do we need to consider besides just how much CO2 it can capture and how stable it is?
Yeah. It's a big challenge.
It is, but it's exciting.
It is.